All right, so let's begin. I think somebody posted a question on one of the forums that there was a typo on in one of the previous lectures on chapter 1. Yuchian or okay, so yeah, so both of those typos are we need to correct them. So this these typos were on this 3-node quadratic element that we were coding up. So finally, okay, that's good. So so yeah, if you take a look at this equation that we were talking about, how to do static condensation for this three node finite element. This is the problem 2 on your homework 4 that I've assigned. Um, In this, I'm asking you to first solve it without using static condensation, and then solve it with static condensation, and you should get the same answer. So the thing that we use for static condensation is called the Schur complement of the bubble functions. So we are denoting this bubble function by the subscript b, and the main functions, the main mesh functions that are connected to the rest of the mesh by m. And if you take a look at this equation right here, all we need to do is to plug this equation into the equation or into the expression for each element. And if you do that, this uh, what we should have here is the main degrees of freedom. So it should be DE3, and instead of the plus, we need to have a minus here. So just make those two corrections, and hopefully everything else is all right. Did anybody else find any other typos or mistakes? Okay. All right. So let me briefly recall what we were doing last time. So we started to take a look at these 2D, 2 dimensions and 3-dimensional problems, and um, we said that just like the way that we were solving 1-dimensional problems, we are going to solve these 2 and 3-dimensional problems using the same sort of mathematical framework. We will write the weak form of the problem and then discretize it and implement it on the computer. So the equations that we were going to be solving for elasticity is this: div sigma plus b is equal to 0 when things are not changing with time. If things are changing with time, then we need to add a rho u double dot mass density times acceleration term in here. Um, and then we took a look at a couple of other relationships that we need: the small strain and the large strain material properties. So for now, we decided to stick with the small strain material properties. And I think this part also might have been missing from your handout. So I just added the boundary conditions. So since this is a boundary value problem, we need to have the boundary conditions also. So this boundary condition just says that the map, the deformation map, is specified on the displacement boundary. And the other condition, this says that Cauchy stress applied to the normal vector of your domain has to be equal to the given traction or given loads that are acting on your structure. So this is gamma d, which is displacement boundary, and gamma n, which is the specified traction boundary. And we took a look at how we are going to actually implement this on a computer. We know that stress and strain are tensors, and they can be represented with matrices. But a different notation that is better for implementing it on a computer is using this Voigt notation. So if you use the Voigt notation, you can actually write your material law, the Hooke's law, in this form. So these are 6 symmetric components of the stress in terms of 6 symmetric components of the strain. And we are going to be using this definition of the engineering strain for this purpose. And if you do that, you can express your matrix for three-dimensional cases like this. We took a look at the plane strain and the plane stress cases. And finally, we started to see how to apply the same principles that of method of weighted residuals to these two-dimensional problems. So we said that since this is actually a vector problem, in which what it means is that we would be trying to find a vector field at every point x. So let's take a look at a simpler problem, which is a scalar problem. And we said that this is a thermal heat conduction problem, where one of the faces of this two-dimensional domain is fixed at some temperature, some high temperature, let's say, and some low temperature at the other end. We are pumping in some heat from here, and this is also actually it's a mixed boundary condition, but this is something similar to your one-dimensional problem on the homework assignment. So this is the given equation, system of equations that we want to solve on this type of a domain. And we took a look at what some of the physical meaning of this is. You have gradient of theta, which is just like our strain. Theta is temperature. Gradient of temperature is similar to strain. Then we have material conductivities, which is similar to our elasticity matrix that we were talking about. And if you plug, and this Q is similar to stress. So this is very similar to the equation that we had that says stress is some function of strain. Okay. And then this is the final equation that we are going to be trying to solve for this heat conduction problem. So we started to take a look at this method of weighted residuals, and we said we are going to do the exact same process. We have this governing differential equation. We are going to define a G which is in this form. We'll take the differential equation, multiply it with theta bar, and integrate it over the domain. Now this domain is a two-dimensional domain, okay? So in general it could be double integral or a triple integral. And if you express the same thing in indicial notation, the reason that I'm trying to express things in indicial notation is because all these quantities with the indices, you can actually expand out, and all of those quantities are going to be scalars. So if you don't see what is the physical meaning of this, you can expand this out and see what are exactly the terms that you are trying to integrate. So now we said that, okay, since this is the form that we also had in the one-dimensional problem, now what we need to do is balance the derivatives. Here you can see that theta comma j and the whole thing comma I. So there's two derivatives on theta. Theta is just a function, the temperature field over the body. And this theta bar, the virtual temperature, if you will, that does not have any derivatives. So what we are going to do is do something analogous to integration by parts in one dimension. So if we do integration by parts, we should be able to transfer one of the derivatives from here to here. And just to make it clear, this comma j denotes del over del xj, right? This is something this is just a shorthand notation that we talked about last time. And comma I is with a different variable, del over del xi. But again, all these terms, they are we are using the summation convention, which means that since there are two i's in this term, we are going to be repeating that term for I is equal to 1, 2, and 3. Similarly, there are two j's in this term, so we are going to be repeating this term for j is equal to 1, 2, 3. So I is 1, j is 1, 2, 3. I is 2, j is 1, 2, 3, and so on. So in a three-dimensional problem, you would have 3 cross 3, 9 terms. In a two-dimensional problem, you would have 2 cross 2, 4 terms. This would be a 4-term scalar expansion. So let's see how we do integration by parts in 2 and 3 dimensions. So just to recall what we did in 1 dimension, we have this product rule that all of us are familiar with. And what we are trying to do here is we'll pick this term. This is the term that is very similar to what we did in the one-dimensional case. and take this to the other side, what we will have here is integral du. Integral du is nothing but the value of this function evaluated at the boundary 0 to L. And this is something very basic that comes straight away from this sort of a equation. If we have a function f, we take its derivative and then we integrate it back again between two limits a and b, right? So all what we get here is fx back. And if you apply the limits a to b, then what you would have here is fb, f evaluated at the point b minus f evaluated at the point a. And believe it or not, this thing is called the fundamental theorem of calculus. So this is fairly simple thing, but there's a big name for these kinds of things. And similar thing happens also in 2D and 3D. So we'll take this sequence of operations and try to write it out in our two-dimensional case. So just like we were considering u multiplied with v in one dimension, we are going to consider this theta. This is a scalar, theta bar, virtual temperature times your heat flux vector. So this is, if you go back here, we had theta bar multiplied with qi, comma I. So this is divergence of q. But what we are saying is we are going to take the divergence of the whole thing, and if we apply the product rule, then we can write it as gradient of this virtual temperature dot product with the heat flux. So this is a scalar, right? This entire thing would be a scalar. A one vector dot product with another vector, that would be a scalar. This is a scalar multiplied with divergence of a vector, that's also a scalar. So this is a product rule for this kind of a two-dimensional problem. And if you write it out in indicial notation, what does it look like? We have theta bar dot with multiplied with this vector. So that's the parenthesis quantity right here. And divergence just means that you take each component of that vector and take its derivative with the x in that direction. So if you apply the product rule once again, what you would have is theta bar comma I, which is the derivative of theta bar, times qi plus theta bar times the derivative of this. So that's right here. And if you were to expand this out without using this indicial notation, what this means is there is two i's, so I need to sum them up for I is equal to 1, 2, and 3. So this term right here is this one, d theta bar over dx times q1, and same thing for 2, same thing for 3. And this term is right here. I can take theta bar out common from each term, and what I would have left inside is the divergence of q. Now, this is the exact same term that we that we have here. We have theta bar times divergence of q. Okay. So all that we are trying to do is we have this term. We will express this term as this left-hand side minus this entire thing. And if you do that, what you get is this. And then finally, if you substitute this back into your weak form, what you would get is this term right here comes here, and I've substituted qi with the kappa ij times the temperature, real temperature, plus theta bar times qi, which is this term. Now this term is extremely similar to what we have here. We know that if we integrate the derivative of some function over some limits, we will just get the same function back evaluated at those limits. So the same sort of thing happens here. This is some function we are taking the derivative of that vector function, and we are integrating it over a two-dimensional or a three-dimensional domain. But we can express this thing in terms of its value at the boundary. So in the one-dimensional case, if let's say the boundary is 0 and L, then in two-dimensional case, the boundary is just going to be the curve around that body. So just going back to this problem, this is the two-dimensional domain that we have, and its boundary is uh, right around it. So what we are saying is, if we have some function, its derivative, if we have the derivative of some function in terms of its divergence in the domain, we can express that in terms of its value on the boundary. That's just divergence theorem, and that's exactly analogous to what we were doing in the one-dimensional case. So this is the aside about the divergence theorem. Um, so what we are saying is, if you have a vector q, you take the divergence of that, that will be equal to q dotted with n, where n is actually the normal vector to the boundary. So what is n? Let's go back and take a look. You have this as your domain, and this is the boundary of your domain. The normal vector is just the outward pointing normal at every point along the boundary. Okay, so all you're doing is take your heat flux vector, dot it with your outward normal. That will be a measure of how much heat is escaping or coming in to your domain. So this is basically just doing math, integration by parts on our problem. And finally, if you do that, you can express this entire thing as an integral over the boundary. Now, in the one-dimensional case, it actually boiled down to the value of the function at the two boundaries. But in 2 dimensions and 3 dimensions, we still have an integral to calculate. We just came down from a 2-dimensional integral to a 1-dimensional curve. Or in 3 dimensions, we came down from a 3-dimensional integral, volume integral, to a 2-dimensional surface area integral. Okay. So this is the term that we get, and plus we have this right hand side, or the boundary, the body force term for the temperature problem. All right. So what did we do at this point when we were doing one-dimensional problems? So at this stage, when we were at the one-dimensional problem, we are at this stage. What did we say? How do we proceed to write out our weak form once we have the boundary terms? Yeah, shape function and all that is approximation, so that will come later on. But we still have some boundary terms where there are a few unknowns, right? And we said that if the displacement is specified at the point 0, then we assume that the virtual displacement is going to be 0 at that point. Does that sound familiar? So we are going to say this almost the exactly same thing here. So what we are going to do is we're going to take this and split it into 2 parts, where one part is gamma d, a displacement boundary, and the another part is gamma n, which is the heat flux or the traction boundary in this case. So if we do that, all that we have left inside is qi times ni, d gamma, and plus the same quantity on the rest of the boundary. So we will have qi times ni d gamma, and we say that on gamma d we are going to choose theta bar to be 0. So this term goes away. This entire term goes away because this is a choice that we are making. We choose our virtual displacement on that part of the boundary where the real displacement or the real temperature is specified. We choose our virtual displacement or virtual temperature to be 0. And once we do that, what we have left here is this term, which is also a force term that will go into the F part of your equation later on. So what finally, if you write out your weak form, what you will have is g of theta comma theta bar is going to be equal to minus all these terms are remaining the same, kappa ij theta comma j and d sigma plus f. Sorry. So plus integral over the domain of the body force term, and since this part of the one part of the boundary term has gone away, we are left with this other part, which is evaluated only over the part of the boundary where heat flux is specified, theta bar times qini. Now, what can we substitute for qini on gamma n? Take a look at your strong form, and so this is very similar to what we had in the one-dimensional problem. We got theta, we used to get u bar times u prime bar. Not u prime bar, but u prime. And we know that u prime is strain times c. So we substituted stress, the actual applied traction, uh, instead of this part. So in this case, it would be this one, h. Q dotted with Ni, Q dotted with N is equal to H. H is the heat that we are pumping in over the part of the boundary that is um, on which the traction, quote unquote, or the heat flux is specified. So if you make that substitution right here, what we get then is theta bar times H over the boundary N. So you can already see where this is going. If you carry out this algebra, you follow this line of thought, what you would get finally is that the discretized version of this, let me call this d vector, d bar, this would be equal to minus d bar transpose times k, the real temperature, minus f vector. And this needs to be equal to 0 for all d bar. So you would end up with this sort of a formulation if you carry out if you continue with this approach. And just take a look at this. This entire term is very similar to what the term that we got in one dimension, which is the internal virtual work, right? And this entire term, this is very similar to the external virtual work term that we got. And if we say that if g has to be equal to 0, then essentially this boils down back again to the principle of virtual work, which says if it is an equilibrium configuration, then for small virtual displacements, your external virtual work has to be equal to internal virtual work if g is 0. Okay, so this is the exact same framework that we used for one-dimensional problems. This is the same framework we are using for heat conduction. We'll use the same thing for elasticity. Okay. Up until all this time, we haven't made any approximations so we haven't made any approximations yet. But in going from here to this point, what we need to do is, what do we need to do in going from this point to this? Discretization, which is in one dimensions, we said we are going to break up our domain into n number of parts. Okay, so the same type of discretization we need to do now in two dimensions. Okay, and let's take a look at what kinds of discretization strategies we can adopt in two dimensions. So let's see if I can bring this up. So again, this is a small MATLAB code. just to show you what a two-dimensional discretization would look like. So we are saying that uh, the length and the width of our domain is 5 and 2 units. So I'm trying to solve this problem. Um, I'm trying to solve, let's say, this problem. This is the domain, 5 is the length, 2 is the width. So I define my domain like that, and we're also saying that we want to discretize this entire domain by having 10 parts along the length, having 10 parts along the width. And that gives me the small lengths like this, and let me actually run the code. All right, so this will create one x vector, x values all along the length for me. So this is, for those of you who don't use the MATLAB debugger or the workspace, this is one of the best ways to try to find errors in your code. Once you execute this, you can actually type the value of x and see that our x values go from 0 to 5 with 10 different values in there. So now uh, this command mesh grid, what it does is it takes these set of x values, set of y values, and it creates this points on this domain. So if you take a look at this domain, I've done 10 parts along here and 10 parts along here, and it creates all these points inside the domain. So let me try to plot those points. And this is the scalar function. This is just a scalar function that I'm defining over my domain. So if I plot, um, right, so this is what I get for my plot. So this is the domain. X dimension is 5, y dimension is 2, and they both have 10 parts in each dimension. And what we are plotting is this function f that I created. So this function f looks kind of like this. Okay. Um, so this function is just a sine of x values and dot. Now, do you know what this is? Dot multiplied y. Right. So it does array multiplication. If you just say multiply without the dot, then it does a normal matrix multiplication. But if you do dot, then it does an array-wise, element-wise matrix multiplication for each of the terms. So this is a sine of x multiplied with a sine of y, y kind of a function, and what it looks like is this. All right, so this is one way of discretizing the domain, right? All I had was this domain. I could discretize it into nice regular mesh. Let's take a look at some other ways of discretizing the mesh. So one way of discretizing a mesh is called Delaunay triangulation. So there is this command in MATLAB. It's already coded up for you. It's called Delaunay triangulation. And if you want to see more information about that, there is this. You can just go in and type Delaunay, and you will come up with this this help page for that, and it will show you how you can create all these triangular meshes. So if we choose the same x points that we generated just now, and if we run this command called Delaunay on that, what we will get back is a set of triangles. So let's see what that looks like. And there's this trisurf command which plots that thing. So this is what it looks like if you discretize it with triangles. You can see that here in this part of the discretization, it was all nice square or rectangles. In this case, they are all triangles. And it's a property of this Delaunay algorithm that you give it any sort of a domain, you can always generate a triangulation of that domain. But you cannot always generate a quadrilateral discretization of a domain. So this is a mathematical result, but so what I'm trying to say here that this is a triangulation that you can always generate. And all this we are doing so that if you go back to our formulation that we were working with, this formulation, right now we are at a stage where we need to calculate all these integrals. So in order to calculate all these integrals, we are going to write this integral as a sum of integrals over all these small elements. And that's why we need to discretize. So that's one way to use a regular triangulation. And now let's take a look at some irregular ways of discretizing. So I will just create some random xy points along my domain. These are just creating some random xy points. And finally, if you plot with that some random xy points, this is the discretization that we have come up using some random xy points. And you can clearly see that in this case, this is a nice regular mesh, and our function looks more or less smooth. If you increase the number of quadrilaterals or if you increase the number of triangles, your solution or your representation of your function will become better and better, right? But in this case, when you are using random points, um, your representation of the function is not that good, right? So it depends upon how you choose your points in the domain. So clearly we can see that right in the center of this domain we have a very high high function value. So it would be better if we choose more points here. And so this is another way of choosing the points. And let's take one last look at a general sort of a domain. These were both square domains. If I create a non-square domain, now this domain I can just define with some points anywhere in the domain, and I can create triangulation for that. So the same function evaluated at all those points, and if you plot the trisurf, if you plot the surface, this this function on this domain, you can see that this domain is not even square. So this is just this is the point that I was making about the Delaunay triangulation. If you have a general domain, you can throw in some points in that domain, ask MATLAB to generate a mesh. Okay. Now these types of things normally we would do in Abacus. You would make a geometry, you would ask it to mesh, and so on. But with MATLAB, there are a few routines that you could use to create these kinds of these kinds of meshes. All right. So so what we'll do now is we'll say that our domain has been discretized into all these different parts, and this discretization is not something that we start out with. This discretization is only after you finally come up with the integral weak form, and now you want to find some sort of an approximate solution. When you want to find an approximate solution, then we want to discretize the domain. So going back to uh-oh. All right, so going back to this formulation, what we will do now is we'll say that using our discretization that we've just talked about, we are going to write our weak form as a sum over elements. This is something that we did in one dimension also. Let's say we divide our domain into m elements, and we are going to write this integral as the sum over elements of, now this is omega e, okay, and the same quantity, theta comma I, kappa ij, theta comma j, d sigma plus the boundary term. This boundary term is also over the elements, and this also needs to be summed up over all the elements. Theta bar times f d omega, and plus, now this is the boundary of the global domain, but I can also split this up into individual boundaries. I don't know why this is skipping on me, but let's see. So sum over all the elements, and for each element you pick out the portion of its boundary, if it is specified boundary or not, and then you take theta bar times the specified heat vector, heat flux vector, and you integrate it over the boundary of that element. So even until this point, we have not made any approximation, okay, because all that we are doing is we are expressing this integral. This integral was over the entire domain. We have just broken up our integral, which was over the entire domain, as a sum of integrals over individual elements. So we have not made any approximation up until this time, up until this point. But now we will introduce our approximation. So let's take a look at some types of elements that we could have. And so one of the elements that we talked about was this rectangular element. And it need not be this nice rectangular element. It could be any type of a quadrilateral. So this is one possibility for the shape of this element. Another possibility we saw was having some sort of a triangular element. And all that we need to do now is to create some sort of an approximation of these functions over this domain. So what we are going to do is we are going to say that our theta, which is a function of x and y, is going to be approximated with some finite element shape functions. So this would be approximated by the finite element solution, which I'm going to denote with theta h, which means discretized. And again, this is a scalar. So all I'm saying is go to any point in the element, go to some point in the element, and try to calculate or try to represent your theta at that point using some approximation. So we'll say that this is going to be equal to sum of some shape functions. Let's call that n alpha times d element e alpha, and where alpha goes from 1 to small n e. So let me explain all these quantities that I'm writing out. So let's consider this square or rectangular element first. Let's call these nodes 1, 2, 3, 4. And in this case, the number of nodes in this element, NE, is equal to 4. Okay. So essentially what we said for this is that the theta h, which is the approximate solution, is going to be equal to n1, n2, n3, n4 times d1, d2, d3, d4 of these elements, of this element E that we are talking about. And once again, we can represent this in the same form that we had represented our one-dimensional displacement. We had this n times d. Does that sound familiar? This is something that we did in one dimension. Um, so this is theta x y. I've not talked about these shape functions yet, but essentially the form of our approximation, our finite element approximation, is exactly the same. The similar sort of thing happens in for a triangular element. Instead of these 4 nodes, the value of NE is going to be 3, and you would have N1, N2, N3 times D1, D2, D3, and you can see that this is a 1 cross 4 matrix multiplied with a 4 cross 1 matrix that will give you a scalar, right? So if the product of this gives you a scalar, then that scalar is the value of this approximation at that point. You go to a different point, then you would have to use the shape functions for that point, multiply this out, you will get an approximate value of theta or temperature at that point within the element. So this is just an approximation that we are making. So let me also show you what type of shape functions we could use. Each of these shape functions, N1 is a function of x and y, and what this looks like is, so let's say this is our element. The shape function at the value 1, I'm not sure how to draw this, but okay, so let's make this, let's say that we are looking at this element from an angle, okay, and the shape function for this first node looks something like this. It goes to 1 at node 1, and it goes to 0 at every other node. This is what the shape function at 1, at this point 1, this N1, this is what it looks like. Obviously it is a function of x and y. Similarly, you would have N2, which is also going to be a function of x and y, N3 function of x and y, N4 function of x and y, and all those shape functions also look very similar. So N2 would look like 1 at the node 2, and it goes to 0 everywhere else. Okay, and N3 would be 1 at node 3, and 0 at all the other nodes. Similarly, you would have N4, the last one, 1 at node 4, and 0 at the other 3 nodes. So these are the types of shape functions that we would be using for this 4-noded quadrilateral element. For a 3-noded triangular element, the shape functions look very similar, but if you will notice, there is a little bit of a curve here in this diagram. If you go from this one node to the diagonally opposite node, this thing is a curve. These things are straight edges, but so this is called a bilinear shape function. But in triangle, for a triangle, if you pick the value 1 here, and if you pick the other 2 values to be 0, then the shape function is actually linear. Okay, there's no curve in this triangular shape function. So using this approximation, what you can do now is you can take this approximation, plug it into our weak form. This is what we are saying. We are saying that if you want to calculate the value or the approximate value of the temperature at some point in the element, that approximate value can be represented by a linear combination of these functions. So this is an unknown solution. These functions are unknown. This is unknown. These are all unknown coefficients. These are known functions. If you take this approximation and plug it into your weak form, you will get the KD is equal to F equation. And let's take a look at that. So the approximate value of the derivative is going to be N this is the approximate value of the virtual displacement, but the derivative is going to be theta comma I. So theta comma I is nothing but d theta over dx1 and d theta over dx2. So this is the derivative of the of our temperature. So this is temperature gradient that we are going to be approximating the same way. And to do this, all we have to do is dn1 over dx1 times dn2 over dx2, dn3 over dx3, dn4, sorry, not x2 and x3 and x4, but these are all x1s. And the same thing here, dn1 over dx1, sorry, dx2, dn2 over dx2, dn3 over dx3. What am I doing? I don't know. So keep on making these mistakes. So dn4 over dx2. This entire matrix is very similar to the matrix that we had for our strain displacement matrix. We are going to call this matrix B. And on the right hand side, we will still have the same vector of unknowns. We will have DE1, DE2, DE3, DE4. So what we have done here is we have approximated our solution with the same sort of formula, n times d. We have approximated our our derivatives with the same sort of formula, which is gradient of theta is v times d. And now if you substitute all this back into the weak form, you will get this equation. So let's stop here, and we'll go through the details of this step on Monday. And on Monday, I guess I'll also talk to you about what we will do about the midterm, which is on the following Monday, February 22nd. Okay? All right. So see you Monday.